Yeah, that's.
All right. Welcome, everybody. Thanks a lot, Eric, for the invitation. And so, as you said, I'm going to talk this afternoon about a weak coupling of two numerical methods for Maxwell's equations. And you'll see the links, I believe, between this talk and Sylvia's talk, because the aim, as you will understand in a few minutes, is to actually couple black box solvers for Maxwell's equations. And I'll motivate this by industrial constraints, actually. And it's also linked with Olaf's talk because it's linked to Maxwell. However, it's not going to be for the quasi-static Maxwell system. It's going to be for high-frequency electromagnetic waves. And it's going to be in a simple setting where we can assume that everything is linear. And so we'll go to the frequency domain. And so that's the reason why the talk is entitled Weak Coupling for the Time Harmonic Maxwell's Equations. This is a collaborative effort. So it's joint work with my colleague Xavier Antoine at the Université de Lorraine in France, and two of our former PhD students, Ismail Badia and Boris Caudron. And they are both with Thales in France, a company that specializes in doing, well, radars, in short. And so I'll show you what it's all about. Can you correctly see the outline? So the slides are moving?
Yes.
Perfect. So I'll start with a short introduction. I'll try to motivate the problem and make the link with what Sylvia was talking about coupling black box solvers. And then I'll have a short, let's say, overview of classical FEM-BEM coupling. I'll re-explain briefly what FEM and BEM are, which is called a strong coupling. And then I will spend most of the talk showing how we try to work in making a weak coupling, that is basically a domain decomposition, efficient for industrial applications. And theoretically, you'll see that the coupling is actually quite simple, but we worked a lot on how to transmit information between the subdomains in order to iterate the least number of times, basically. And then I'll show you some numerical results, some extensions, and an actual industrial application. All right, so what's the setting? So my setting is, as I said already briefly, transmission and scattering of electromagnetic waves. So E and H are my electric and magnetic fields. In the simplified setting I'm considering here, I have a scattering object that I call omega minus. Keep in mind for the remainder of the talk that it could be homogeneous, but just for validation purposes. But the aim is to actually treat a scattering domain, omega minus, that is non-homogeneous. So I parameterize my Maxwell system using impedances Z and wave numbers K. So for the rest of the talk, the goal is to have Z minus and K minus to be spatially variable. Then outside of omega minus, we are going to assume that Z and K are constant. And so typically in all the applications I'm going to show, omega plus is air. And then if we start with that, we assume that we have an incident electromagnetic wave. So to keep things simple, we can assume that we have a plane wave, so E inc. And then your electromagnetic fields defined in the outside domain omega plus. You have your time harmonic Maxwell system, so recognize the curl equation with the wave numbers and the impedances posed in omega plus and omega minus. To make the whole thing well posed, you have a Silver-Muller radiation condition and infinity. And importantly, so I haven't introduced notation yet, but in between omega plus and omega minus, I will call the interface gamma. And on gamma, you basically ensure that the tangential components of the electric and magnetic fields are continuous. And so that's my setting. And so this is the kind of problem I want to solve. And so how do you solve this? Well, it's a very classical problem, but still it is difficult, even though it is linear. So why is it difficult? Well, first of all, it's the domains that we need to consider are unbounded. So that's a given for the applications that we're targeting. Think about radars. Then it's the full Maxwell system, so it is intrinsically vectorial. And most of all, as you know, if you go to higher and higher frequencies, which are dictated by applications, then somehow you need to resolve the wavelength with whatever numerical technique you choose to use. And so you either need to go with very fine discretizations or very high orders in order to capture the highly oscillatory behavior of the solution. So people have been solving such problems for a long time. And the two, let's say, common approaches, if you target this Maxwell system in the frequency domain, is to use, well, FEM, so finite elements, in which case, well, you have to be careful. So first of all, for FEM, so for finite elements, you need to truncate the computational domain. So this introduces an approximation at the continuous level already. And then classically, you write your weak formulations in truncated domain, you discretize. And in addition to the truncation, let's say, issue, you need to be careful about the fact that if you use low order FEM, you know that for highly oscillatory solutions like the ones you'll get for the high frequency Maxwell system, then the solution will exhibit quite large numerical dispersion. And so to alleviate that, you go to higher order usually. The second method that you might use, but only if omega minus is homogeneous, so if K minus and Z minus are constant, or at least piecewise constant within omega minus, you would go to integral equations. And so for us, since omega minus is supposed to be non-homogeneous, you could use integral equations for the outside domain. And so this, as you know, at the continuous level, it will be exact. You end up with a surface problem. So at the discrete level, you only need to discretize the boundaries and you use boundary elements. And since, let's say, the long-range behavior of the solution is encoded in your Green's function, numerical dispersion will be less of an issue. So typically for BEM, you can stay with, let's say, relatively low-order elements. So it's completely natural, of course, if you compare FEM and BEM, to already think about the coupling. So let's just review FEM versus BEM, the advantages and disadvantages. The advantage of FEM, large sparse matrices once you discretize. BEM, you have dense matrices, but for the last 15 years, you have efficient compression methods, so fast multipoles, H matrices, so you can get away with your dense matrices. For FEM, you are well suited for non-homogeneous domains. BEM, homogeneous domains or piecewise homogeneous. FEM, you need the volume mesh. BEM, just a boundary mesh. FEM, you need to truncate. BEM, it's ideal for unbounded domains. FEM, high numerical dispersion. BEM, only low numerical dispersion. So where do we come from an industrial point of view? So as you saw, two of the, let's say, co-authors of the talk are with Thales in France. They design radars, and they also build in-house BEM codes. So their code is called antenna design, or AD in short. And of course, AD is not well suited for handling anisotropic and non-homogeneous materials. However, in the new designs that Thales is doing, they use, for example, materials with spatially varying electromagnetic properties, which makes BEM, well, not ideal, because you basically need then to make assumptions and to simplify the problem. For example, changing, let's say, smoothly varying electromagnetic property and making it staircase with relatively large steps in the staircase in order to do then BEM on the interfaces. So that's not ideal. So the natural idea is, of course, to couple AD, so the BEM code from Thales, that is accelerated with an H matrix library called HiBox. And you would use that for the homogeneous parts of the system. And then you couple that with a FEM code. And as we saw, if you want to target high frequencies, you need high order FEM. And so for this, a natural choice for us, because we develop it, is to couple AD with GMesh FEM, which is a finite element code for high order elements that is built on top of GMesh. So how do you do that? Let's first review the natural first way of coupling FEM and BEM, which actually goes back to what Olaf just showed for the quasi-static Maxwell system. You can do exactly the same for the full wave system. You need to define the trace operators, and you basically arrive to a natural, strong FEM-BEM coupling formulation. You would have where you would have within omega minus a classical finite element formulation in terms of the electric field. And then on the boundary gamma, you would have a coupling with a classical integral equation. You actually have several choices for this, but this is a classical choice that was already proposed more than 30 years ago. If you do it like that, you end up with a linear system where you have basically sparse and dense blocks, which is perfectly fine until you want to go to high frequency calculations. Because your FEM sparse block and the dense BEM blocks, what do you do with them if you really want to target large scale applications? And here we're talking about applications where you need to go to cluster computers, HPC machines. And so how do you basically solve, let's say, these problems? You need to go to iterative methods. And the fact that you have an operator here with sparse blocks and dense blocks, well, there is a case to be made where you would like to basically just use black box solvers for the FEM part and the BEM part, because you have existing efficient solvers for the two parts. Whereas, well, if you consider the whole coupled problem directly, brute force, then how do you combine, for example, the compression techniques, say FMM, H matrices, for the coupled, let's say, system directly? So that's not quite clear. So, and again, if you want to minimize the effort, which is paramount actually for industrial applications, so how do you reuse existing optimized solvers if you do the strong coupling? It can become quite technical. We actually did it. And yeah, you need to actually modify, let's say, the solvers, maybe not dramatically, but significantly. So a simple solution, which is also a natural solution, is to just consider a weak coupling between the inside, let's say, problem solved with FEM and the exterior problem solved with BEM. And the natural framework for that is to use domain decomposition. And we come back to Sylvia's, let's say, abstract formulation for this. So you'd like to couple these two solvers as black boxes, iterate, and design a preconditioner or design the iterations in such a way that you minimize the number of iterations. Because, of course, at each iteration, you basically need to solve, again, the FEM and the BEM problem. So the method that we chose is basically a Schwarz method. If you conceptually have a look at such a method on a toy problem, here a scalar wave propagation problem, you would subdivide your computational domain into subdomains. You would define interface unknowns between subdomains I and J that we call here G, I, J. You would need to solve in each subdomain the local problem using your black box solver. And then you'll need to update your interface unknowns and exchange information between the subdomains through transmission operators that we're going to call Tij. If you have a look graphically, when you iterate, you basically exchange information between the subdomains. And the aim is that after as few iterations as possible, you end up with the solution of the full problem by assembling the solution of all the local problems. So how to do this with FEM-BEM? Well, first of all, actually, it's clearly not new. And so 2007, 2008, you have seminal papers on this by Bendali, Boubendir, and collaborators that have proposed already a Schwarz-type coupling between FEM and BEM using what I will call in the next slides low-order transmission or coupling operators. The method was analyzed formally. It works great, but it takes a lot of iterations to converge, or potentially takes a lot of iterations to converge. And so basically our extension is to try to use the same setting, 2 subdomains only to start, 1 FEM domain, 1 BEM domain. Use a Schwarz method, no overlap. You use generalized, as you will see, Robin conditions between the subdomains, so very classical. But then you work on the transmission operators, so on the information you exchange between the subdomains, to try to minimize the number of iterations that you will make, because each iteration entails a local problem solved, which is expensive. And so the first step towards achieving this was done by Boris Courdron in his thesis. So sorry, it's in French. So couplage FEM-BEM faible optimisé pour apprendre la diffraction harmonique et acoustique en électromagnétisme. So this was done in 2018. And there you have the theoretical study and the first numerical tests, but for acoustics. And there was the premises of the electromagnetic case. But more recently, we continued with Ismail Badia in his thesis, again, sorry, in French, that basically extends the results to electromagnetics, and that goes all the way to applications and high-performance computing. So how does it work? So this is the core of the message that I want to convey to you this afternoon. So it's basically an optimized Schwarz TDM, which means that it's going to be a Schwarz method, but where the conditions that you have on the interfaces, so the exchange you do between the subdomains, you're going to actually use more complicated operators that are assumed to approximate the DTN, or in this case, the magnetic to electric operator of the complementary of the subdomain. Our setting is simple. Remember, we have 2 subdomains. And so we're going to try to approximate the exact MTE, magnetic to electric, operator from the complementary, so for the other subdomain compared to the one that we are talking about. So this is the parallel with the previous 2 talks with the Steklov-Poincaré operator that we talked about. In order to see how different operators behave in this Schwarz coupling, well, I need some notation. So I'm going to use T minus and T plus to label my transmission operators. And these are the transmission conditions. I haven't defined T minus and T plus yet. You'll see that we have several choices for them. But if you look at the way the transmission conditions are written on gamma, so the interface between omega minus and omega plus, you see that these are basically impedance type or generalized impedance type boundary conditions, or Robin type conditions. Instead of having just here a scalar, you have an operator. So they link the magnetic and the electric field, their traces on the boundary, through operators T minus and T plus. The unknowns that we'll have, remember, in between the subdomains, we'll exchange some data. Well, the unknowns are linear combinations that in between H and E, the electric and magnetic field, that involve these transmission operators T minus and T plus. And in what follows, I'm going to call the local solvers, so the FEM solver and the BEM solver. I'm going to basically abstract them as resolution operators. R minus for the FEM solver, so basically the operator that sorry, computes G, the data in the interface, given E on the boundary. So through this resolution operator R minus. So that's for FEM. And the BEM solver, I call it basically R plus. So that's the operator that, given E on the boundary, can compute G, the data to exchange. And then you can rewrite your coupled problem like this, where you impose on the coupling boundary that the trace of H plus or minus the trace of E that to which you apply the transmission operator is equal to G. So if you reformulate this in an abstract way, it's a linear problem, and you see that this iteration problem, you can actually write it as an affine formulation here, where you have the identity and an operator that we call S pi. This operator S pi involves these operators S plus and N minus that involve both the transmission operators and the resolution operators. And this is the abstract, let's say, affine system you want to solve in terms of G minus G plus, the data on the interface of interest, so gamma. Right? So why do we formulate it this way? You see that it's not totally classical. It's not a linear system. It's an affine system. We do it because this way, in an industrial context, you also hide the sources within the black boxes. This is not so trivial because if you consider the target problem that we have, where you might want to model a radar, for example, with FEM, with the outside domain with BEM, well, the radar might be developed by one company, not to name it Thales, and the outside, which is basically a plane, will be designed by somebody else. Let's not name it, let's say Dassault. And so how do you exchange data if you want to couple codes from these two industrial partners that might not want to share all the details about the sources, in addition to not sharing the details about the codes and the geometries? Well, that's the way to do it. You basically formulate the problem like this, where your affine operators contain the contribution of your sources. More than hiding the sources, in my first, let's say, toy cartoon picture, I suppose that gamma was on the boundary of the scattering object, the inhomogeneous object. This is, of course, not necessary. Not necessary. Sorry, you can choose gamma, and typically, as you'll see in a few minutes, you would like actually to choose gamma to have some regularity, and this is also good for industrial cooperation because it allows you to basically hide other geometrical details that you might not want to share. So what does a simple algorithm look like for the problem? You could imagine doing a Jacobi iteration. You don't do that in practice, but it gives you the idea of how it could work. You basically solve the two problems for the outside and the inside in parallel at the same time. And then you update the unknowns using the S plus and S minus operators. Again, these operators, they entail the resolution and the transmission of information. So you can go back to a linear operator setting. That's easy. It's all a linear problem. So I'm trying to skip this or go through it really fast. So you can rewrite the contribution of the sources this way. Basically introduce a little variable with a little tilde. The slides, I can make them available if you want to look at the details. But basically, you can repose this whole thing as a classical linear system where you have, instead of S pi, you have this operator A, you have your coupling unknowns G minus G plus, and the right-hand side that depends on the sources. It's easier to analyze if you put it that way. In practice, you never build the operator over here, the linear operator. You basically use a Krylov subspace method, such as GMRES, to solve this iteratively. And the only operation that you have to do is basically compute the forward map, so the application of this operator on one iteration of the interface data, G minus G plus. All right. So this is the actual algorithm. So you compute the right-hand side. You factorize the matrices associated to the subproblems, and then you do the matrix-free solution of the linear system that is associated to the weak coupling. After convergence, you apply once more the resolution operators to go back to the field that you're interested in, E in this case. So if I draw this schematically, we have only two subdomains, omega minus, omega plus, and at each iteration of your, say, GMRES, you solve the interior and exterior problems at the same time. Then you update the unknowns using your operator A that entails the resolution of the two subproblems, and you get the exchange information. What do you use for the resolution operators R plus, R minus? Well, you have a choice. For R plus, we use a classical formulation for electromagnetic scattering. And for R minus, we use a standard finite element formulation. So these are the two, let's say, formulations that are implemented in the black box solvers. And for this formulation here, we actually don't have the choice because that's the formulation that's implemented in the Thales code. The choice you have is actually on the operators T plus, T minus. And so what do you choose? Well, as I said already before, what you would like is to actually get close to the magnetic to electric operators that are defined as follows, that basically map E to H, or conversely, H to E. Why? Because if you think about it, if you look at the operator T minus, and if you take it to be minus the MTE corresponding to the outside, then you get this S plus operator that is actually 0. And if for T plus, so the transmission operator plus, you choose the MTE for the minus part, so for the interior, then you get S minus to be 0. If you do these two choices, so if you choose T minus to be minus the MTE for the outside and T plus to be the MTE for the inside, then you get A equal to 0, which is normal, right? Because you have the exact solution, basically, in the complementary of the subproblem that you are considering, A equal to 0, meaning that you basically converge in one iteration. So this is what you'd want. But you don't need this. And so this is the first main point of my talk today. With these two subproblems, actually, you don't need to have both, let's say, operators that are close to the MTE. And this is actually difficult. So think about it. If you look at the interior problem, you have a complicated non-homogeneous scatterer. It can have like billiard type, let's say, interactions in there. So it entails complex non-local interactions. Computing actually an accurate approximation of the MTE for the interior is a really tough job. It will stay morally non-local. The outside problem, on the other hand, is much easier, and it has a mostly local behavior. And so the first idea of the lecture here is to say, if you want to do the coupling of these two black box solvers, then you should use a precise representation of T minus only, because that's easy. You can choose T minus as basically minus lambda plus. You cannot use the actual lambda plus because this will be costly. It's a non-local pseudo-differential operator, but you can do, let's say, efficient and accurate approximation of this lambda plus. And for T plus, well, actually, you don't really care. You can use a rough approximation of it, because if T minus is a good approximation of minus lambda plus, then A will be nilpotent and you will get fast convergence. So by just having one operator that approximates correctly the MTE of the complementary. So that's the first, let's say, main idea. So still, even if it's, let's say, easier to do the approximation of the outside operator, well, there have been quite a few approximations proposed in the literature. And so I'm reviewing some of them here. So the one we are going to use is based on an approximation of the MTE by micro-local analysis that we did, well, 8 years ago with Mohamed El-Bouajaji and Xavier Antoine. It is based over here, you see, on the inverse of the square root of the operator over here that involves the vectorial Laplace-Beltrami operator on the boundary. I'm not going to go into all the details because it gets quite technical quite fast for Maxwell, but you should get the gist of the method. And then you can consider also simpler approximations. Actually, you could use a 0th order approximation of this, which is basically just a constant. It would lead to a classical Robin condition on the boundary. And you can use what we will use in practice, Padé approximations of the operator of various orders. And so if you want to increase the accuracy of the approximation of the MTE, we'll go to higher and higher orders of the Padé approximation. I'm not going to give you all the details because they can get a bit messy. So just for fun, I showed you the actual formulation that is implemented in the coupling layer, where you actually implement this approximation of the MTE. Having both codes for the two subdomains as black boxes is fine, because these two, let's say, black box codes need not be modified, but you need to write the glue in between. In the form here, we chose to do it using finite elements on the boundary to represent, let's say, this approximate MTE operator corresponding to the outside problem. Okay. All right. So let me show you how this works in practice. So for the FEM solver, we use GMESH-FEM, so a high order FEM library from Liège based on GMesh. And for the BEM solver, we use TMOS code, so BEM PPCL, for the first tests. Right. So this is because the eventual goal, I'll show you later, is to use AD from Thales, but to do a bit of numerical analysis and testing, it's actually nicer to have an open source code to be able to deploy it on our own computing clusters and do simulations. So we use BEM-PP. So BEM-PP is in Python, GMesh-FEM is in C++, but again, it doesn't matter because the coupling that you do is independent of the two local solvers. I'm going to show you results for different choices of the pairs T minus T plus. With what I said before, you should already have the intuition that, well, basically you need to choose for T minus a good approximation of minus lambda plus, and the rest you won't care. So I'll show you that. I'll show you results for two academic problems, sphere, which is dielectric, and a cube with a missing let's say 1/8. And these are non-homogeneous scatterers because the wave number k minus and the impedance z minus basically is spatially dependent on x. X is the spatial variable. And so you see you have some kind of a Gaussian, let's say, behavior of the wave number and the impedance in these two scatterers. And so this is how it is done. You need a coupling layer, so you don't touch GMesh-FEM and you don't touch BEM-PPCL, but you write a little glue that we call GMesh-DDM, which is actually a more general domain decomposition library, where you write the weak formulations that, let's say, allow you to handle these interface unknowns, so G plus and G minus. And this is the only thing that you basically play with, GMesh-DDM. You don't touch the two black box codes. In order to make this work, as I alluded to before, you need high-order basis functions for each curl to reduce the pollution effect in the FEM part. That's standard. So we use the basics functions from Pavel Solin and co-authors. You store the factorization of the matrices. With BEM-PP, we didn't use any acceleration. So this is brute force, let's say, BEM and squared complexity. With AD, then you'll have, let's say, storing matrices in the H matrix format. And the code here, since you do not touch the two black box solvers, you need somehow to encode the representation of data. This is what Sylvia talked about in the beginning of her first talk, where she talked about informatics and the way to do it in practice. Well, in practice, GMesh and BEM-PP don't have the same definition of the degree of freedom, so you need it's a coupling matrix. And so this, you need to do the job once to basically transform the conventions from one code to the other. But this is done, again, outside of the two black box codes. This is what you get. The captions are still in French because these are results from the PhD thesis of Ismail Badia. And so you look at the number of iterations for the Krylov solver, in this case, GMRES. Here, the first result in terms of the contrast. So this is delta is the electromagnetic contrast between the outside, so air, and the inside, this inhomogeneous scatter, normalized in some way. I'll give you the reference in the SIAM where you can get all the nitty-gritty details about how, let's say, the problem is parameterized. We use fairly low number of points per wavelength because this is actually enough for the BEM part. And then we use high order 4, for FEM inside, which is okay. And then you look at the number of iterations, and what you see is that if you do old style FEM-BEM coupling, so circa 2007, 2008, where you would use actually here the black curve, the lowest order approximations for the transmission operators T minus T plus. So you use T minus equal to minus lambda plus 0, so 0th order approximation of the outside MTE. And for T plus, you use a 0th order approximation of the MTE for omega minus. And you see that you have clearly a dependence with respect to the contrast. And you also see a behavior that is, well, not quite regular. And you see these peaks that appear. If you look, this is for the sphere, you have pretty much the same behavior for the cube with the corner. There are other test cases in the paper that you can examine, but all the test cases behave in the same way. The cube is just worse. So you see that if you increase the contrast, you'd have the number of iterations that grows quite dramatically. We capped the number of iterations to 200. So here, it's not that it converged at 200, but it's just that we stopped GMRES at 200. In order to get better behavior, let's look at other pairs. So again, on the left, you have T minus. Here you have T minus chosen as minus lambda plus. SQ is the little shorthand for our Padé approximation with fourth order numerator denominator, okay? And you see the difference directly. We look at the black curve, we go to the blue curve. So just choosing one of the two operators, T minus, to be a good approximation of the exact MTE actually gets you already pretty nice results. However, you still see that for some values of a contrast, you have an increased number of iterations. You can get better by choosing for T plus minus lambda plus 0, so minus the lowest order approximation for the outside domain, which seems a bit weird, right? Which means that for the transmission operator T plus, which ideally should entail the most precise approximation of the interior MTE, we actually choose minus a rough approximation of the MTE for the outside. The analysis for this is not done. This is just an observation, but actually it's much better. You could somehow morally have an intuition about why it is better, because actually it's almost like when you look at the interior problem from the outside, if you take as a transmission condition something that is as if you were looking at the inside made of the same material as the outside, you have like a transparent boundary. So this might explain why you don't see this, let's say, behavior where the contrast still appears, whereas if you look at the pair that we will eventually choose, you see that you have an almost independent of the contrast behavior. For the cube, same kind of story. You see that the behavior is actually extremely nice. You see a slight dependency of the number of iterations with respect to contrast. Let's continue. We can now look at the behavior in terms of frequency, or here in terms of wavelength. So the interior wavelength actually is linked to the exterior if you look at the parameterization. So it's sufficient to plot this in terms of the outside wave number. And you see that whereas with lower approximations, you have a slight for the sphere, but quite a big dependency with respect to frequency for the cube, then you see that with the appropriate, let's say, transmission operators, at least with T minus taking as, let's say, the approximate, the precise approximation of the outside MTE, you get something that is almost independent of frequency. If you look at mesh refinement, the story again is the same. You see that using an efficient representation for, well, an accurate representation for T minus leads to almost independency with respect to mesh refinement. So next question is, we couple these two black boxes, we iterate. We saw that using appropriate transmission conditions, numerically, you can get a low number of iterations. You still need to know when to stop. So I didn't tell you when we did stop GMRES for the previous tests. Now let's have a look at where you should stop. Basically, what you see here first is the accuracy that you have. Depending on the contrast, you said it's okay. But what is interesting is to look, for example, as a quantity, to a quantity of interest for industrial users, which is RCS, or in French, SER. So for both objects that we just considered, if you look at the RCS, or the radar cross-section, you'll see that depending on the tolerance you put on your Krylov subspace solver, you see that, so this is clearly not enough, right? This is GMRES converging just to a relative error of 10 to the minus 1. You see that you need to go to 10 to the minus 3 to not see any more differences on the computed RCS, which tells you that for these kind of couplings, for these ranges of frequencies and for these obstacles, actually you can stop GMRES relatively early and still have a very good, let's say, accuracy on the quantity of interest, which is here the far field through the RCS. So in addition to what we discussed, numerical tests show you that the choice of the discrete approximation of the unknowns is important. There is no analysis for this yet, but you have observations. And typically what we saw is that choosing G, so the interface unknowns, in H-1/2 div, so using basically facet elements on the boundary, seems to be the best choice, even though since we increase the order on the boundary as well, it's not dramatic, the influence, but the numerical results show that it's a bit better actually to choose G plus minus this way. You still need to increase the FEM order inside for E minus to reduce dispersion error. And what we saw is that the fictitious extension of the exterior problem within omega minus by choosing T plus to be minus lambda 0 plus is actually a good idea. So if you want to know more about the details, all the results are explained in this SIAM JSC paper from this year, just published. So the numerical recommendations that we have for this coupling: the best operator pair, the accurate outside MTE for the T minus operator, the 0th order approximation corresponding to the outside for T plus, Padé with order 4, and the rotation of the branch cut by pi over 2. I didn't talk about this. You have the details in the paper. Numerical tests show that a GMRES tolerance of 10⁻³ is enough, and it's recommended to have a regular exchange surface. So let me show you one extension that is important for industrial applications that doesn't change anything with respect to the black box nature of the two solvers. You'd like to be able to deal with metallizations and partially metallized objects, which lead to open exchange surfaces. You can deal with that in two ways, either, again, in a strong way by enforcing that your interface unknowns are imposed to 0 on the metallization, or you can do it in a weak way by canceling out this approximate MTE operators. And actually both work quite well. The weak way is actually numerically seen to be slightly better. This, again, is something that we need to analyze because it's not completely understood yet. And finally, because I'm running short, I'll show you one application that shows you really the power of this methodology on an industrial application. So here we switch from BEM PPCL, sorry, Timo, we switch to AD, coupled with the H-matrix high box library. So this is in Fortran. Again, it doesn't make any difference. And this is a case, I cannot show you the actual industrial case, but it's close. Let's say where we choose the case to have piecewise homogeneous materials within omega minus in such a way that you can also validate the simulation using a full BEM code. We choose the things that I just explained for T plus T minus, the pair of operators that we just discussed. And we go to increasingly complicated applications. So first, a metal cylinder surrounded by dielectrics, and you check that it works just perfectly fine. And you converge, this is the important number to remember, in 16 iterations. So it takes 16 times, let's say, the solution of the local problems to converge to, let's say, 10 to minus 3 in relative error in GMRES. You can do the opposite kind of little test case where you put a metallic cylinder outside and a dielectric inclusion. You see the kind of far field that you get, and you get convergence again in a number of iterations that is completely reasonable for such industrial settings. You can do multi-layered dielectric cylinders. You get again the same kind of behavior. And then I'll finish with this kind of application, which is already a bit more realistic. You take a dual band polarizer. You illuminate it using horn antennas in 2 frequency bands. And this is a typical complicated problem to handle if you were to do it fully using a single solver, because for BEM, you have very thin regions for the metallization, the thin dielectrics, and you have already quite a bit of geometrical complexity. You have all these unit cells that are, let's say, stacked next to each other. And so you basically compare the solution using gains for the right-hand side and the left-hand, let's say, polarized solutions. And you basically get the same kind of behavior. So it shows you the robustness of the approach. You again converge in very low number of iterations. And if you compare with, let's say, all different, let's say, teams that have tried to solve this problem, because this is a problem that is part of a, let's say, public workshop where, let's say, industrial users and developers of software compare their code, you see that the weak FEM-BEM coupling performs extremely well. The most important part is about computing time, and let me show you what it does. So if you use a full BEM code, you basically, for, let's say, a decent mesh that gives you an industrial, let's say, the industrially relevant error level, it takes for one frequency 4,000 seconds. If you use weak FEM-BEM with 0th order transmission conditions, it takes about 3,000 seconds. And if you go to, let's say, the new conditions that we designed, you basically divide by 2, which is a nice, let's say, result, because you only have 2 domains here. So you still have quite a large cost associated with, let's say, the FEM solution of the interior problem, whereas the outside problem is accelerated. But the conclusion is that your weak coupling is actually significantly faster than, let's say, the full BEM code for comparable accuracy, and that using, let's say, more accurate transmission conditions between your black box solvers is significantly faster than, let's say, the older order 0th order conditions. Okay, so I'm running late, so let me conclude. So I showed you one practical application of what we learned about at the beginning of the afternoon with Sylvia's talk. It's for time-harmonic Maxwell equations. I showed you a way to get the number of iterations under control. So the number of iterations here is only slightly dependent on the geometrical configuration, the frequency, the refinement of the mesh, and the contrast between the subdomains. And the weak nature of the coupling, this is the main message, allows you to use untouched the optimized solvers for both subdomains. The computational performance I showed you is basically competitive for industrial grade applications. Perspectives, actually, here are some preliminary results. If you don't want to pay the extra cost of doing Padé to get accurate representation of the magnetic to electric operators, you can also do higher orders, let's say in Fourier space, polynomial approximations. This is quite classical, including or not a rotation of the branch cut. And you see that you are, as expected, in between. So this is, let's say, the best approximation that we can do for now locally. You get 9 iterations. The 0th order operation, you get 29. If you do second order polynomial approximations, you are in between, let's say, the best and the worst. If you really want to go toward industrial problems, of course, you need to decompose the interior domain as well. This entails some, let's say, issues that were alluded to in the first talk, and you have cross points. And so there are ways for, let's say, these high frequency problems to do this, at least using the high order operators if the subdomains are split, let's say, in regular manners. So basically with right angles between the partitions. In the general case, you also have solutions, but with different transmission operators, which will lead to actually more iterations. So there is still an open question for this. For all the gory details, these are the 2 papers you can have a look at. So the first paper with Boris for the acoustic case, which contains the ideas and the analysis for a simple case, and the paper for Ismail for the electromagnetic case. And with that, I conclude, and I will be happy to answer your questions.